Hi guys, and welcome to GT Algebra 2. So I'm Mrs. Baker. For now, you're probably just going to hear my voice on these videos. We'll actually meet after I am done with my maternity leave and I come back. I know it's kind of a weird way to start the year, but this is kind of a weird year to begin with. So we're going to make this work. I think it's going to go really well. It's just going to look a little different this year. So what we're going to do today is we're going to start with just really an overview of all of the characteristics and vocabulary that we're going to use throughout the year for all these different functions. So Algebra 2 is really nice because it's a very kind of organized course to where each unit, typically you're doing a different function. And with that function, you're going to do some similar things. You'll do some solving, some graphing, some things that are unique to that function, some applications, but really every unit is kind of its own function. And you'll really see that take shape the most in second semester. This first unit, we're going to look at one of those functions, which is absolute value, and kind of do some of that stuff with it. We're also going to kind of lay the groundwork for things that you'll see repeated throughout the year. So today is really actually a pretty important day because today is going to go through a lot of vocab that you're going to see just throughout this year. It's going to come back over and over and over and over again. So it's a really important day to understand. So what we're going to start with is really notation. So until this point, you've probably not seen something that's called interval notation. And interval notation is a really big one. It's one we're going to use consistently throughout this year. It's the one you're going to see most often in your math classes in the future as well. So all we're going to do to start is compare interval notation to inequality notation. So inequality notation is the one that you saw back in Algebra 1 more than likely. So we'll start with just some words, okay? So it says all real numbers from A to B, including A to B. So the first thing we're going to do is we're going to describe that interval. And what we mean by describe is just say, is it either bounded or unbounded? So bounded intervals have a clear start and stop point. Unbounded intervals, at least on one side, are going to continue towards infinity, all right? So it doesn't have a stopping point on either one or both sides. So this is a bounded interval because it's going from A to B. So the way that you would write that in inequality notation is A is less than or equal to X is less than or equal to B. What this would look like as a picture is, let's say here's A and here's B and there's a number line. So that's kind of what it looks like graphically. So set notation or set builder notation, that one may be new as well, but this one's actually really simple if you've been using inequality notation. Really, it's just a different look. And this is going to come up a lot more when you get into statistics or some of your math later on in life. You'll see this set builder come up. And what you have really is just telling you which variable, and then it's kind of describing the features of that set. Now, sometimes you may also see an additional piece. You may say something like X, this little sideways thing that kind of looks like an E, and then another symbol, followed by whatever your domain is. What that means basically, X, that's saying that X is an element of all real numbers. You can make that more specific later on in life, like you may make that integers or whole numbers or something like that. But we're not going to get to that much in this class. So really for you guys, set notation, it's going to give you the variable. Okay, the whole thing is in those curly braces. And then after that bar, you've got basically your rule. So really simple if you know inequality. Interval notation is the new one and the big one. So the way interval notation works, it basically, when we're talking about domain or we're talking about just an interval in general, we're going from left to right, and we're going to use either parentheses or brackets to show our endpoints. Parentheses mean the point is not included. It means we get as close to that point as we possibly can, but we don't actually touch it. So on a graph, that would look like an open circle. Okay, a bracket would be a closed circle, okay, a point that you actually touch. Now, it doesn't have to be a closed circle, all right? It could be, let's say I have something like this. Well, there's not a definitive closed circle on that point, but it does touch that point, okay? So that point would be, again, that bracket for that closed circle. So the way that we would describe this, since these points are included, we're going to use brackets, and we would just say bracket A, comma B. Once you get used to it, interval notation is going to be a lot faster and a lot easier. And again, this is the one that's going to come up a lot in your future math classes. All right, so now the next one, all real numbers greater than A. Okay, so we're basically saying from A, everything that's greater. So this is an unbounded or infinite interval, okay? It keeps on going forever. So in inequality notation, we would say that those numbers are everything that are greater than A. So set notation, I would just have x is greater than a. So in interval notation, again, the smallest value here comes first. So the smallest value is a. It's not greater than or equal to, so I'm going to use a parenthesis. And then it keeps going until infinity. Our infinities will always have parentheses because you can't actually touch it. We get as close to it as they possibly can. All right, our next one, all real numbers less than or equal to a. So here's a, and it's all numbers less than or equal to it. I should have done an open circle on that picture. Make that a little bit more clear. There we go. All right, so this is an unbounded interval because, again, it keeps going to infinity on one side. There's an arrow, basically. In inequality notation, I would say that x is less than or equal to a. Set notation, my brace, x, and then x belongs to that set where x is less than or equal to a. So in interval notation, the smallest value that's listed here is negative infinity. Then it keeps going until it reaches a. It actually touches a, so we got a bracket on it. All right, looking at the next one. So this time it's just giving you the picture. Okay, so again, we'll go smallest to biggest when we get to interval notation. This is a bounded interval because, again, it's not a matter of open and closed circles. It's a matter of there is a start and a stop point. So in inequality notation, -3 is less than or equal to x is less than 4. Set notation, very similar. And then in our interval notation, I would put a bracket on -3 and then a parenthesis on 4. All right, so if you feel pretty comfortable with this, go ahead, pause the video, and actually try the next couple on your own. All right, so let's look at the next one. That is an unbounded interval. In inequality notation, this is going to be that x is less than or equal to 3. Set notation, again, very similar to our inequality. That looks like a y, but that is, in fact, that's not a 4. That should be a 3. Sorry about that. Looking at the question above. Then in interval notation, this would be from -infinity to 3 with a bracket. All right, next one. This is a bounded interval. Because again, even though it doesn't touch those points, it does start and stop. So this would be from -4 is less than x is less than 6. Set notation, again, going to look really similar. Whoops. And then in interval notation, these would both be parentheses because we don't actually touch those points. We'll get to 5.9999999999999, but we will not actually get to 6. We'll get as close to it as we possibly can. All right, then this last one, this one is unbounded. Now, inequality notation on this one's a little different. I can say x is less than 4 or x is greater than 4. I kind of have both of those things. X is just not equal to 4. And that's the nice thing about Set Builder is because it allows me to actually say something like x is not equal to 4. So it's a little bit simpler to use there. Set notation is also really good if you have a discrete set. So you only have like a few points, and you can just say like x is 2, 3, and 7, if it's just those discrete values or something along those lines. All right, then we've got our interval notation. So what we'll do here, well, again, we're going to start with the smallest value, which is -infinity. Then this graph continues until 4, but it doesn't actually touch 4. So 4 has to have a parenthesis, but my graph doesn't stop there. So what I will do is I'm going to put a U for union. Then I'm going to pick back up at 4, and I'm going to keep going to infinity. All right, so what we're going to do now is we're actually going to continue to work on interval notation, looking at graphs. All right, so we're going to find domain and range using our graphs. So to start on these, we're going to do inequality notation, because that's what you guys have done before, but then we're also going to write that domain and range using interval notation. So on this first one, let's start with our domain. Okay, domain again is left to right. So our farthest left x value is -3. It is touching that point, so it's an or equal to. Then the farthest right x value is 5. Then let's go ahead and do range. Range is going to be bottom to top. So the lowest y value here is -1. The highest y value is 3, and it touches that in more than one point. That's okay. So that's my domain and range. So now we're going to write this in interval notation. So interval notation, we're going to see some similar numbers. Again, left to right, farthest left point is -3. We keep going to 5. Range, bottom to top, the lowest y value is -1. The highest y value is 3. Now, even though there's an open circle here, that doesn't affect our range because this graph does still touch that y value. So even though there's an open circle, it's okay because your graph does still have a defined point there. All right, the last thing it says is to tell whether the graph is a function. So if you remember from Algebra 1, for functions, your x's do not repeat. Okay, every x has exactly one y. So this graph is a function. All right, let's go to our next one. Domain, we'll start with inequality. So I have x is less than or equal to -4. And I also have that x is greater than 3. For range, now let's look at the range here, okay? This graph is going to keep going all the way down to -infinity. This part of the graph is going to keep going to +infinity. Even though there's an open circle here and your graph stops here, those y values are still going to continue to be touched past those points. So your range here is all real numbers. So in interval notation, okay, the way we'd write our domain, the farthest left is -infinity. It keeps going until -4. We actually touch and have a defined point at -4, so it's a bracket. Union, then we pick back up at 3. And then we continue to infinity. Range, on the other hand, we touch every possible value, so my range is -infinity to infinity. And this graph is a function. All right, looking at the next one, we'll start with domain. Now, looking at your domain, you see there's a little bit of a skip here and a skip here, but even though there is, every x value is still included. So there's a defined point here at 1, and then we get as close to 1 as we possibly can. So even though this graph is what we say, it's not continuous, the domain is still all real numbers, or -infinity to infinity, because it touches every single possible value. The range, again, even though there's some jumps and some skips happening here, we still touch every single y value above that y value of 0. So the way we'd write that in interval notation is from 0 to infinity. And then this graph is a function. Now, it's not continuous, and we'll get there in a second, but it is actually a function still, because none of your x's repeat. That's why you have that open and closed circle there. All right, then looking at this last one, okay, starting with domain. So again, if I look left to right, there's kind of a jump here and this gap here, but the points are still defined on that region. So your domain here is -infinity to infinity. Range, bottom to top, a little bit different this time. So our lowest y value, this graph keeps going for forever, is -infinity. Then it keeps going until the y value of 0. It actually touches that point. Again, it doesn't have like a clear dot, but it obviously touches it because there's no open circle there. So I put a bracket. Then it continues, it picks back up at the y value of 3, actually touches 3, and keeps going to infinity. Now this graph is the first one we have that is not a function. And the reason it's not a function is because there are 2 y values right there at the x value of, looks like 4. Oh, sorry, 3. So there's 2 y values there. Now again, it means your domain is -infinity to infinity, but this graph is not actually a function for that point. All right, so we're going to move on to some new vocab now. So what we're going to look at now is something called end behavior. So end behavior really is just exactly what it sounds like. It's what are the ends of your graph doing? So what we're going to do is we're going to write 2 statements for end behavior typically. We're going to say what happens as x approaches -infinity. And then we're going to look at what happens as x approaches +infinity. And what we care about is as x approaches -infinity, what we're going to fill in is what is y approaching. So let's look at this first graph. As x approaches -infinity, as x gets smaller and smaller and smaller and smaller. So this graph, as the x's get smaller, you'll notice your y's are getting bigger. They're getting larger. So your y's are approaching positive infinity. All right, then let's look and see what happens as x's get bigger. So as this graph goes to the right, as those x's get larger, those y values are continuing to get smaller. So my y values are approaching negative infinity. All right, let's look at the next one. Again, we're going to write two statements. As x approaches negative infinity, so the left of my graph. So as your x's get smaller and smaller and smaller, your y's are getting smaller and smaller and smaller. They're approaching negative infinity. As x approaches positive infinity. Okay, as x approaches positive infinity, those x's are getting bigger, then you can see that those y's are getting smaller. Those y's are approaching negative infinity as well. Now, it's not always going to approach positive or negative infinity. A lot of the graphs we look at this year will, but it doesn't have to. So here's an example that you probably saw in Algebra 1. If you don't remember, this is an exponential function. So this exponential function has this horizontal asymptote on it. So let's start with the first one. As x approaches negative infinity. So if you guys remember from Algebra 1, that horizontal asymptote, basically your graph gets really, really, really close to it, but doesn't actually touch it. So that means as your x's are getting smaller and smaller and smaller, your y's are getting closer and closer to that asymptote. And since we're saying what the y's are getting closer to, we're saying that the y's are getting closer to 0. Then as my x's are getting bigger, as my x's are getting larger and larger and larger, my y's are also getting larger and approaching infinity. All right, then let's look at this last one here. So again, as x approaches negative infinity, what does y approach? So as my x's are getting smaller, they're approaching that horizontal asymptote. Horizontal asymptote has a value of 3. All right, as x approaches positive infinity, as your x's get bigger and bigger and bigger, they also approach the horizontal asymptote at 3. Now, it doesn't matter that one of these is above the asymptote and one of them is below the asymptote. It just matters that's what it's approaching. Now, this idea is going to be really helpful in behavior. We're going to look at that throughout this year, but you're going to see this come back in pre-cal and in calculus as well. You're just going to use a different notation and start to look at the concept of a limit instead. All right, so another concept that's going to come back in pre-cal and in calculus as well. We're going to talk about minimums and maximums. Now, you've talked about what are called global or absolute mins and maxes before. All right, that is just the absolute highest or lowest point on the entire graph. Some graphs don't have these. Some graphs do. Bounded graphs could have both. What we're also going to introduce, though, is a concept called a local or relative max and min. And what that is, it's not the highest point necessarily on the entire graph. It's the highest or lowest point relative to the points around it. So what this looks like on your graph is what we call a turning point. All right, it's where your graph really, it's going to look like the top or bottom of a curve. So let's look at this first example. I'm going to show you guys 3 points. So here's 1, 2, and 3. So all of these points are what we call relative or local extrema. And that just means min or max, okay? Extreme is kind of your generic term to mean either one. So what we're going to do is we're going to be more specific on quantifying those points. Now, what we use them for kind of depends on how your question's asked, okay? If you want to know where it is, that's the x-coordinate. If you want to know what the actual value of the min or max is, that's the y-coordinate. Now, for today, we're just getting used to what these points are, so if you just label the ordered pair, that's fine. But going forward, we do need to pay attention to what our question's actually asking for. If it wants to know what the value of the min or max is, that's your y-coordinate. If it just wants to know where it is, well, that's your x. So let's go ahead and classify these points. Well, let's start with the blue one. Okay, the blue one, that is the absolute minimum of the graph. It is the lowest point on the entire function. Okay, nothing will ever be lower on that graph. Now that green point, though, it's not the highest point on the entire graph. But if you notice, it is the highest point relative to those points that are closest to it. It's the top of a curve. It's a turning point. Your graph changes from going up to going down. So that point right there is what we would call a relative or local maximum. So that relative and local term, they're really going to be used interchangeably. Same thing with absolute and global. You'll hear both in this class, you'll hear both in calculus. So then this last point down here, okay, again, it's not the lowest point on the entire graph, but it's the lowest point relative to those points closest to it. So that is going to be a relative minimum or a local minimum. Now this point over here that we marked as an absolute minimum, it's also a relative minimum. But the absolute minimum, I mean, that's the only absolute minimum we have on that entire graph. So it is both of those things. All right, let's go to this next one. So again, we're going to look for any relative or local extrema that we have on this graph. So this graph actually has a common mistake on it. Sometimes people think there were 3 extrema on this graph. There's actually only 2. This point and this point. This point in the middle here, it is a special point. That's something called a point of inflection, but it is not a relative min or max. The reason for that, your graph doesn't, if you notice, going through that point, your graph is still moving down. It doesn't change from going up to down. So that's not actually a turn in your graph. Now it bends kind of slightly, and we'll get to point of inflection here in a little bit, but it's not an extrema on our graph. So this point up here, again, it's the highest point relative to the points around it. So it's a relative maximum. It's not the absolute maximum. This point down here is the relative minimum. It is not the absolute minimum. This graph does not have a relative min or max on it. An absolute min or max on it, just relative. All right, so now let's look at our last one. All right, so our last one here, we have a couple different features we can find. So let's start with this point here. That point there is a relative maximum. It is not the highest point on the graph. Okay, it's the highest point relative to those points around it. This endpoint over here is the absolute max or global max. It is not a relative max though. And the reason it's not a relative max is because when we actually talk about the actual definition there, we're looking at the points around it on both sides. If you notice though, there are no points to the right side of that graph. So we can't say it's higher than the points relative on both sides because again, there's nothing to the right of that graph. So it is the absolute highest point on that graph, but it's not relative because we can't look at both sides. So if you get a bounded graph, those endpoints of those bounded graphs will not be relative extrema. They could be absolute, but they will not be relative. So that leaves us just with this point down here, and that is our relative minimum. So this point over here is nothing. It's an endpoint, which is important for us, and we refer to say it's a bounded interval, we'll use that point, but it's not the highest or lowest point relative to the points around it, because there's no points over here to compare it to, and it's not the absolute highest or lowest point on the entire graph. All right, so our next one. This is, again, talking about interval notation. So I apologize, guys, that today is a longer video. Most of them will not be this long. Today, since it's such a big introductory day, there's just a lot of vocab to get through. So I apologize that it's a bit on the long side. Most of them will not be this long. I'm warning you now. All right, so again, when we talk about intervals on a graph, whenever we use that terminology, we're talking about the x values where something is happening. So if I talk about a graph and I say on the interval 0 to 7, that means from the x value of 0 to the x value of 7. And that's some terminology you're going to see a lot going forward in your math classes. So the first intervals we're going to look at are increasing and decreasing intervals. So the way this works, we look at our graph from left to right. So as we follow our graph from left to right, if the y values are getting larger, then the graph is increasing. If the y values are getting smaller, the graph is decreasing. Think of it as positive slope and negative slope. Okay, if it has a positive slope, it's increasing, a negative slope, it's decreasing. Where it changes from increasing to decreasing, those are our relative mins and maxes. So let's start with this first one. So I doctored this graph a little bit. There is actually an arrow there. But as I look left to right, even though that arrow is going down, I'm reading this graph left to right. So as the x's get bigger, the y's are getting bigger. So that section of my graph is increasing. I'm going to write that in an interval notation. And even though we're talking about the y's getting bigger and smaller, when we list intervals, we're always going to use the x values to list the intervals where it's happening. So this is happening from negative infinity to 1. Now, the question here about parentheses and brackets. I will tell you guys, you will have different classes potentially in your future, some that will use parentheses and some that will use brackets at this point. It gets really specific on the definition of increasing and decreasing. I'll tell you, as far as I know, both are usually kind of considered okay for increasing and decreasing. But for this class, we're typically going to use parentheses for our increasing and decreasing intervals. In a future math class, you may use brackets at those points. And again, it's just getting into the specifics of the definition. For now, we're really just getting used to writing the interval and recognizing where these things are true. We're not going to get into the very specifics of the definition. All right, now let's go to the next section of my graph. The next section of my graph is decreasing, because as those x's get bigger, the y's are getting smaller. So from 1 to 3, it's decreasing from the x value of 1 until the x value of 3. All right, then let's look at the last one. Well, I already put the union there, so you know. That last section is increasing. So from 3 to 5, your graph is increasing. All right, the next part is talking about where the graph is positive and negative. So again, where it is we're going to list the x values in the interval notation. But again, it's referring to what your y's are doing. When are your y's positive? So when your y's are above the axis. So that's the part I just highlighted in yellow. So this graph is positive from 0 to 2. 0 to 2 are going to be in parentheses, because when x does equal 0, y equals 0. 0 is not a positive number. 0 is 0. This graph is also positive from 4 to 5. At 4, we're going to use a parenthesis, because at 4, the y value is 0. But at 5, I need a bracket, because this graph is bounded. So at 5, the actual y value there is a positive number. So I've got a bracket on it. All right, then let's go to our last part, negative. So negative, again, is going to be this part that's below the axis. So that part that I highlighted in green there. So this graph is negative. Again, we're listing x values from negative infinity to 0, and then again from 2 to 4. We're going to use parentheses on those because, again, at those points, your graph does not have a negative value. It has a value of 0 or, again, infinity. All right, if you feel comfortable, pause the video, try this next one on your own. All right, so let's go to this next one. So increasing, I want to go ahead and just label it or draw on here. So it's increasing on this part right here. That is from negative 6 to negative 2. Decreasing, okay, that's that part I highlighted in green. That's from negative 2 to 2. And you may have been wondering, well, what about this section right here? So that is not increasing or decreasing. We actually use a different word. We say it's constant. So you know how we kind of talked about slope, how this is kind of a positive slope and this is a negative slope? Well, if the 0 slope, okay, it's constant. So this graph is constant from 2 to infinity. All right, positive and negative. So positive intervals is from here to here. And then on this one, if you were to do this on your own, you might have just estimated. I do want to go ahead and actually find what those actual points are, because I want to just review some Algebra 1 stuff real quick and make sure we just all kind of remember this. So again, this is part of what's making this video a little bit longer, but I really want to make sure we have kind of this stuff down because it's kind of our baseline for the year. So in order to find this point, I need to know what this line is. In order to know what this line is, I need the slope and the y-intercept. So this graph has a slope of 2. If it had a y-intercept, it would have a y-intercept of 7. I want to know this value here when y is 0. So I'm going to solve that equation, and I get negative 7 over 2. So that actual point there is negative 7 over 2. All right, let's do the same thing on the next one. Let's actually find what that line is. So that line, we know it has a y-intercept of negative 2. And then the slope here is a little bit harder to see. But that slope goes down 5 over 2, and there's a y-intercept of negative 2. So again, I want to know what this point is. So I want to know when y equals 0. That was not an eraser. So I get that x is equal to a negative 4/5. So now I actually know what those points are, and I can be specific about these intervals. All right, so this graph is positive from negative 7/2 to negative 4/5. This graph is negative basically everywhere else, but we need to be, again, we're going to list the x values. So it starts at the x value of negative 6. At that actual point, there is a negative y value, so we can use a bracket. It continues until negative 7/2, picks back up at negative 4/5, and then keeps staying negative until infinity. All right, so we are almost done with our vocab. Again, apologize, this is a longer one, but a lot to get through today. So a lot of this part's review. A lot of this is actually Algebra 1 stuff, so just making sure we understand function notation. So to evaluate f of 2, that means when x equals 2, what does y equal? Well, when x equals 2, y equals 3. Because again, the open circle means that and we don't actually need to write y equals 3. I'm just going to say f of 2 equals 3. That open circle, you do not actually have a point there. It means you get as close to that point as you possibly can. All right, find all values where f of x equals 1. That means when y equals 1. That happens at two places. When x equals negative 1 and when x equals 1. All right, average rate of change. That is, again, something from Algebra 1, but this one might be a little bit different just because of the notation. Okay, average rate of change is another word for slope. So this is saying what's the slope on this interval. Remember, interval, just like we did for positive and negative, interval is telling us x values. It's saying from this x value until this x value. So from the x value of negative 2, well, on my graph, that's this point right here, until the x value of 0, that's this point here. So once you can read this, it's a really easy question. It's just saying what's the slope between those 2 points. And between those 2 points, that's the slope of negative 2. All right, this last question we talked about briefly because we actually used this same picture for domain and range. Just wants to know where this function is discontinuous. So what that means really in simple terms, there's a lot more complicated definition, but in simple terms, if I'm drawing this graph, where do I pick up my pencil? Well, I had to pick up my pencil here, and I had to pick up my pencil here. So there are 2 places where this graph is discontinuous, at x equals 1 and x equals 2. But what we're going to get into is the specific types of discontinuity. So the first type of discontinuity is a removable discontinuity, or a hole. Okay, so a removable discontinuity is pretty special. This is going to come up a lot second semester. What that looks like, we call it removable because it's going to look something like this, where your graph still gets really close to that point, but it keeps on going. It's removable because let's say I filled in that point, all of a sudden that graph is continuous. So this is a really special one. So that's a removable discontinuity. Another type of discontinuity is an infinite discontinuity or a vertical asymptote. So again, in Algebra 1, you saw horizontal asymptotes when you did your exponential functions. An infinite discontinuity or a vertical asymptote, again, it's very similar, it's just vertical. But your graph at a vertical asymptote is going to keep going either up to positive infinity or keep going down to negative infinity. Doesn't matter which one, doesn't matter what's on what side, it could be both. But that's what a vertical asymptote looks like. The other type of discontinuity is a type we just saw in the previous graph, and that is a break or a jump. So what that looks like is your graph is doing one thing, and then you kind of jump up to another point and do something else. And that's the one you're going to see probably most common this first unit. The infinite discontinuity and the removable discontinuities are going to come up a lot more second semester when we do rational functions. All right, so this graph, not a great picture. I will tell you, it's hard to find good pictures for these. But let's just first find the points where our graph is discontinuous. So one of those points is negative 2. Another point is 2. Another point is 4. And the last point is at 6. Well, let's talk about what's happening there. At negative 2, that is a jump or a break. Because again, your graph jumps from this point down to this point. The fact that this point is here, that doesn't really affect, it's still discontinuous. It doesn't really affect the type of discontinuity. That point could be there, it might not be there, doesn't change it. X equals 2 is also a jump. X equals 4 is an example of an infinite discontinuity or vertical asymptote, because you can see at that point your graph is going up to infinity. Then the last one is also a jump or a break. All right, looking at B, this graph has 3 places where it's discontinuous. 1, 2, 3. And each of those is a different type. At x equals -1, you have a jump. At x equals 1, you have a whole or a removable discontinuity. So that's what a removable discontinuity looks like. What makes it different than the jump, if I fill in that point, my graph is now continuous. With that jump, if I fill in that point, it's still not continuous, okay? I would have to make this whole line connect, and then it's not a function. So there's a big difference between those two. And then the last one, it's not marked. We'll say it's x equals 2. That would be a vertical asymptote or an infinite discontinuity. All right, so we are almost there, guys. So this next part, even and odd functions. This is another one that's going to come up a lot throughout the year. And there's 2 different ways that you can tell if a function is even or odd. One of them is by looking at the graph and looking at symmetry. The other one is just doing it algebraically. So we're going to start with symmetry. So if a graph has y-axis symmetry, it is an even function. So the picture on B, if I were to take that graph and flip it over the y-axis, it's the same thing. So that is an example of an even function. Origin symmetry is an example of this first one. So this first one would be an odd function. Origin symmetry is, again, if you reflect it over the origin. What that kind of looks like is if you reflect it over the y, and then you also reflect it over the x. So if you reflect it over both, you end up with that same picture. And I know it's kind of hard to draw, but that's what that will look like. All right, so algebraically, you can also figure this out. So algebraically, what we do is we replace x with -x. So let's look at the first one. I'm going to replace x with -x. All right, well, -x squared, if I take a negative times a negative, it's a positive. If I do -2 times -x, that becomes plus 2x. So now I need to determine a couple things. If I end up with the exact same original function, then this is an even function. Well, if I look at this, this is not the exact same as the original. One was plus, one was minus. The other possibility is if I end up with the negative version of that function. Well, the negative version of that function would be a -x squared plus 2x. Well, that's not the same thing. So this function actually is neither. And that happens actually pretty often. Even and odd are pretty specific and pretty special. Not every function will be odd or even. A lot will be neither. All right, let's try B. So let's evaluate f of -x. All right, if I take -x and raise it to the 5th power, it's going to be a negative still. This would be -4x to the 5th. Well, now that is the negative f of x. The same thing as the original function, the negative version of it. So that means that this function is odd. All right, then looking at C. Let's go ahead and evaluate this by plugging in -x. So this would become, if I use -x to the 4th power, that becomes x to the 4th. And I end up with the exact same as the original function, which means that this is an even function. All right, finally, we have reached the end. Again, I know this will not be the length of most of your videos this year, guys, I promise. But there's just so much vocab in this first day. What's nice about these questions, too, there's a lot of explanation here, but the actual problems are really quick once you get used to it. So the explanation process takes a lot longer in the beginning. Again, most of your videos will not be this long. All right, so we're going to talk about concavity, okay? So when we talk about concavity, you probably saw this back when you did parabolas and quadratics in Algebra 1. A parabola that opened up actually is something called concave up. Your parabolas that open down are something called concave down. Kind of the way I was always told to remember it, concave up looks like a cup. Concave down looks like a frown. What's actually happening there, if it's concave up, it means the slope is increasing on that graph. And I know it's kind of hard to think about slope on a parabola, but think if you were to draw kind of a line, kind of tangent to that graph at different points, and look at what's happening to your slope, that slope is constantly getting bigger. Okay, let's say this is a -7. This is a -1/2. This is 0, 1/2, 7. So as that graph goes on, the slope is increasing. So that's concave up. Concave down looks like a frown. The slope is decreasing. Now, where your graph changes from concave up and concave down is called a point of inflection. So that point that we saw when we were talking about relative mins and maxes, that was a point of inflection because your graph was changing from concave up to concave down. All right, so again, a lot of information here, a lot of vocab. Once you get into this, though, the actual problems will be pretty quick. And again, this is stuff that's just going to come up all year. So really just kind of trying to lay the groundwork here for some things you're going to see throughout the year. But that is it for today. Thanks for hanging in there, and good luck.